Today, we're going to talk about the stability of Lagrange points. So first, let's talk about motivation. Why should we look at the stability of Lagrange points? Isn't it enough to go over to Wikipedia and see that the L1, 2, and 3 points are unstable, while the L4 and L5 points are stable? Well, the thing is, there's a deeper story to it for both the collinear and for the equilateral points. Let's start with the collinear ones. Usually when we think of unstable, we think of the idea of a ball at the top of a hill careening off to infinity at the slightest disturbance. What the dynamics around the collinear Lagrange points actually look like is more like this, where, yes, at the end of the day, solutions are unstable and they will careen off to infinity. But when you start close enough to the Lagrange point, and with the right conditions, you actually circle around the Lagrange point for quite a while before you go off to infinity. And with some minor corrections, you can stay circling around that Lagrange point for quite a while. By doing the stability analysis, we're going to be able to come up with equations that will allow us to come up with the initial conditions that will get our spacecraft circling a Lagrange point. So, a couple of prerequisites. In order to get the most for this video, you'll want to have a good understanding of Taylor series expansions. If you're not familiar with these, I highly recommend this video by 3 Blue 1 Brown. Even if you are familiar with them, it's worth a watch. 3 Blue 1 Brown has great content. The other thing you'll need to be familiar with is linear stability analysis. I don't have a specific resource to recommend for this one, but I'm sure that a smart, good-looking viewer such as yourself will have no trouble finding one. Okay, with that out of the way, we need to do a little bit of prep work before we can get started with our stability analysis. Let's first copy over the equations of motion that we found at the end of the last lecture. So we want to do 3 things to these sets of equations to make them a little bit easier to work with. We want to non-dimensionalize them. We want to do a coordinate change. Specifically, these equations are all centered at the barycenter of the two-body system that we happen to be studying. We want to change the coordinates so that they're centered around a Lagrange point. This makes the stability analysis a little bit easier because we can check to see if the solutions go to 0 as opposed to checking that they go to a specific point. Lastly, we're going to want to rewrite these equations in the form x dot equals f of x, where in this case x is a state vector, and I'll get into that in a second. The reason we want it in this form is because many theories of stability analysis are centered around equations that fit this formula. This is also going to be useful for numerical integration later on. Non-dimensionalization, this is going to help make the equation a little bit easier to work with because we're going to use it to get rid of the theta dot and the g in these equations. And also, it'll make the equations conform to what you'll see if you read any papers or such about the circular restricted three-body problem. Everybody uses the non-dimensionalized equations. So let's start with that one, non-dimensionalization. So non-dimensionalization means we want to work with a unit length, which I'm going to call m star as like meter star, and unit time, which I'm going to call s star as second star. So let's first start by non-dimensionalizing the length. So we're going to say that L, the distance between the two primaries, is 1 meter star. So L is equal to 1 meter star, which is equal to, in the case of the Earth-Moon system, for example, 384,400 kilometers. So we're going to introduce a new variable, x non-dimensional, and it's going to be equal to xs divided by L. For these first 2 things, the non-dimensionalization and the coordinate change, I'm just going to work with the first equation, and you can try on your own to apply to the second 2 equations. So if we substitute, so note that xs is then going to be equal to Lx non-dimensional. So if we substitute this value for xs in here, what we're going to see is we're going to have L times xn non-dimensional double dot minus, now remember that R13 and R23, those have xs values in them as well. So from the last lecture, this is how we define those. So we're going to end up pulling an L out of here. And the x1 and x2, we're going to non-dimensionalize those as well. So we're going to have x1 non-dimensional is equal to x1 over L, and same thing for x2. Basically, we're going to pull an L squared out of here, and out of here, and out of here, and then we have it out of all of them, so square root of L squared is L, and then it's going to be L cubed, because remember, all of these quantities down here are cubed. So we're going to have R13 cubed. I should write ND here because this is now, like, since we pulled the L out of R13, it's technically not the same equation as this R13, but I'm just going to leave it the same just so that there's less to write, and hopefully you understand. So then we're going to pull an L out of this as well, minus GM2 over by L minus 2 non-dimensional. Okay, so notice that this L is going to cancel out of all of them. Now, we still have an L cubed in the denominator, but we'll get to that in a second. Right now, let's take a look at theta star and non-dimensionalized time. So, sorry, theta dot, not theta star. So if we notice from the last lecture, we know that theta dot is equal to the square root of the gravitational parameter of the system divided by L cubed. So I'm just going to write that. Actually, let's write it out. G. Now that's going to be in units of radians per second. So we want a non-dimensionalized time, and to get rid of theta dot, we're going to make it equal to 1. So that means that our non-dimensional time has to essentially make this equal to 1. So to do that, we'll say that the number of seconds in a non-dimensional second is going to be equal to the value of theta dot. We're going to use S star like we used meter star for here. So this basically means that since these all cancel, we're going to end up that theta dot is equal to 1 radian per unit second. Remember, this is the circular restricted three-body problem, so theta dot is constant. Lastly, we want to get rid of g. Now, how are we going to do that? So g is equal to 6.67 e to the minus 11th meters cubed per kilogram second squared. Let's start by non-dimensionalizing the seconds. So we see that one non-dimensional second is equal to this many dimensional seconds. So we'll just multiply that out. So since there's a squared sign here, we can get rid of the radical. So this is going to be L cubed over g by m1 plus m2. To get rid of the g, and let's note that this is a second squared divided by 1 second star squared. So to get rid of the g, we notice that here we have a g, this is in the original units, and this one is in the original units. And because this is in the denominator and numerator, these basically go away. Now, I know that looks tautological, like we're saying g is equal to g times 1 over g, so, it disappears, how wonderful. The math does work out, trust me. This ends up giving us L cubed. If we divide by L cubed on both sides, we're going to end up getting that squared. There's no units on the top anymore because we got rid of the meters, and it so happens that g over L cubed is exactly what we have in these equations. Now we can rewrite this equation and substitute g and theta. So since I'm left-handed, let's do it this way. So we have x non-dimensional is equal to... Now I'm going to introduce a new variable, and this is one that you'll find in literature for the circular restricted three-body problem, and it's going to be mu. So mu is going to be equal to m2 divided by m1 plus m2. So it's the mass of the smaller primary divided by the total mass of the system. Now, even though we use mu here, don't confuse this for the gravitational parameter, because sometimes we refer to this quantity as mu as well, the g times m1 plus m2. This is the same letter, but a different concept, so just be aware of that. So notice that 1 minus mu is equal to m1 over m1 plus m2. And also notice that x1 non-dimensional, we said that was equal to x1 over L. Well, we defined x1 in the previous lecture as m2 over m1 plus m2 times L. So the non-dimensional version gets rid of the L, and then we just have mu. So we can say x1 non-dimensional is equal to mu. And then by similar logic, we can say x2 non-dimensional is equal to 1 minus mu. So let's go ahead and rewrite all of that. And like I said, I'm not going to do this for the y and z equations out here, but you can do that on your own and get some practice. So let's go with the coordinate change. So we want to change the coordinates to have the center, the origin of our system of equations be at the Lagrange point. as opposed to at the very center of the two-body system. So for that, I'm going to introduce a new variable, and I want to get rid of all these subscripts that we're using, so I'm just going to call the new variable x. It'd be nice to call it something else. We only have so many letters in the language, and it's just, for the rest of this series, I want to refer to x, y, and z as the position, and then their derivatives as velocity. So we're just going to say x is now just going to be the position of the spacecraft. So we're going to say x is equal to this x non-dimensional minus Lx, where Lx is the non-dimensional x-coordinate of the Lagrange point. And so then we'll also have y is equal to y non-dimensional minus Ly, and then z is just equal to z non-dimensional. So note, by the way, x dot is equal to x non-dimensional dot, since this is a constant, so this just goes away when we take the derivative. So let's go ahead and rewrite our equations with this in mind. R13 cubed. Now R13 is going to change as well, and I'll get to that in a second. I'm going to keep the same name just so that there's less to write, and that is an R and not an N. R13. And so here, x, y, and z, they're now the distance from the Lagrange point. And I'm using Lx and Ly instead of giving specific values so that we can basically change the origin later on. So as we do the stability analysis, we'll essentially change the origin to various different Lagrange points by changing Lx and Ly. So like I said earlier, this is going to help us because when we do the stability analysis, we'll be able to check to see if solutions go to 0 as opposed to checking to see if they go to some particular point. And it also makes the Taylor expansion easier because we can just Taylor expand around 0. Let's take care of R13. So that's going to be, let's reference our previous slides. So like we had before, we non-dimensionalized all of these. So remember, x1 becomes mu, x2 becomes 1 minus mu, and x becomes x plus Lx. So it's going to be x plus Lx squared plus z squared. And R23 is equal to square root of x plus Lx minus 1 minus mu, that whole quantity squared plus y squared plus z. Oh, sorry, that's my mistake. This should be y plus Ly squared plus z squared. Okay, and lastly, x dot is equal to f of x. Yes, I know it's unfortunate that we're using x for a lot of different things. Notation can get really confusing with this stuff, but we just kind of power through it. This x is not this x, it's a state variable, it's a state vector. So if I were on a computer, I might treat this as capital X and bold it, and leave this one lowercase and unbolded, but it's a little bit hard to do that over here, so we're just sort of going to live with this for now. This x contains that little x, and it's a vector containing x, y, z, x dot, y dot, z dot, and we're going to treat it as a column vector. So I wrote it as a row vector, but you transpose it and you'll get the column vector. So then that means that x dot is going to be the derivative of x, so that's just x dot, y dot, z dot, x double dot, y double dot, z double dot. Again, transpose. Now we want to write things in this form. And like I said earlier, that's going to make it possible for us to do numerical integration later on. And also, many of the stability theories that we're going to look at have been designed around equations of this form. That's gonna make things very easy for us. Writing it like that, the first three terms, we're basically going to write this vector as a function of this other vector, and we're going to do it component-wise, component by component. So the first three are going to look a little strange because we're just going to see that x dot is equal to x dot. Basically, I'm just saying this x dot from here is equal to this x dot from here. So there's really nothing much there. Now we get to the more interesting part where we write x double dot is equal to, basically we're rewriting this equation so that we only have x double dot on the left hand side and everything else is on the right hand side. So that's easily enough. Minus, oh, there should be a negative sign here. My apologies. And here. Yep. And here. Yeah, there, we still have it there. Okay. I'll go ahead and write out the equations of motion for the other two variables. Okay, so now that we've gotten the prep work done, we want to analyze the stability of these points. In general, there's two ways to analyze systems of differential equations. There's Lyapunov stability analysis and there's linear stability analysis. There's also graphical methods such as phase plane plots, but we're not going to consider those. So Lyapunov analysis works well because it applies for both linear and nonlinear systems, but it's a bit lacking in terms of what we're looking for because it can only tell us if a system is marginally stable or stable. Stable in this case meaning asymptotically stable, but it can't tell us if a point is unstable. Linear stability analysis can tell us these things, and it can give us that richer picture of dynamics that we're looking for, but it doesn't apply to this system because we have nonlinearities in here. Specifically, the nonlinearities are coming from these terms because we have, we're looking for the solution x as a function of time. Here we have, 1 over the square root of x of something plus x squared cubed plus this. So this is nonlinear, right? So what we'll have to do is we'll have to do a Taylor series expansion of these three equations to linearize them about the origin, about the equilibrium point. And then we'll be able to do a linear stability analysis. Now, it's important to note that by the Hartman-Grobman theorem, we can analyze the linearized system and still reach conclusions about the nonlinear system. So, to quickly recap linear stability analysis, we're looking to see where the poles are on the complex plane. If all of the poles are in the left-hand side of the complex plane, then our system is stable. If a single pole, if any pole is in the right-hand side, has a positive real part, then the system is unstable. If the system has poles that are on the imaginary axis, i.e. they have no real part, then in a linear system it would be marginally stable. But when we do the linearized analysis and we find that the linearized system has points along this axis, then we can't actually reach any conclusions about stability because we don't know if the higher order terms of the Taylor series that we've ignored, if the higher order terms are going to push those center points to the left or to the right. But the point is that doing a linearization using Taylor series expansion, we can still reach conclusions about the original system. It just depends on what we find. So with that said, let's go ahead and perform a first order Taylor series expansion of all three of these about the origin, and then that's going to give us a set of linearized equations that we can then find the poles of and do our linear stability analysis. Okay, so now we're going to start doing Taylor series expansions. So to do the Taylor series expansion, I'm going to make a note that x double dot can be considered to be a function of x, y, z, x dot, y dot, and z dot. And likewise, y double dot is equal to a different function of x, y, z, x dot, y dot, z dot. Similarly for z double dot. And because these are different functions, I'm going to give them these subscripts to indicate which function I'm referring to. So fx of all this is this equation, fy this equation, fz this equation. Now you'll notice that we don't use all of these variables in all of these equations. Like for the example, the z one, it does have x, y, and z in the r13 and r23 terms, but it doesn't have x dot, y dot, or z dot. In fact, none of them have z dot. But I'm just writing it this way for completeness sake. So to do the Taylor series expansion of a function, it looks something like this. I'm going to use this notation. I'm going to write big capital T, and we're going to say which function we're expanding. So it's going to be f of x and about which point, and it's going to be the point 0. So this expansion means that we evaluate fx at 0. And in this case, I'm using 0 as a vector. So essentially, we're saying all of these are 0. Then we would take, because we have multiple variables here, we want to take the derivative of fx, the partial derivative with respect to x, and we want to evaluate that at 0. And then we're going to multiply it by x. And then we're going to add the derivative of fx with respect to y, evaluated at 0, multiply it by y, and so on. So let's go ahead and take care of a few easy ones first. First of all, you'll notice that fx, this is going to be 0. Why is that 0, and how do I know that without doing the evaluation? I mean, if you look at it, it looks like there should be an Lx term here, right? Well, this is an equilibrium point. Remember, we decided that we were changing these coordinates such that the origin is an equilibrium point, which means that x double dot is equal to 0. So it's 0 by definition, but if you do plug things in, you will find that all those terms cancel and x double dot will in fact be 0. So that one goes away. That's really easy. Then we know that there's no dz dot, so the derivative with respect to z dot is going to be 0. And we know that there's only a single y dot here, so this one actually becomes pretty straightforward because the derivative with respect to y dot ends up being 2, and then it's being multiplied by, so this ends up being, it's just 2. We're evaluating at 0, but it's just a constant 2, so this whole term ends up being 2y dot. So you'll notice when you do the expansion, the linear terms stay the same. Oh, one other thing I should note, actually, just for the sake of completeness, is that technically with a Taylor series, we keep going, right? So this is a first order Taylor series, but a full Taylor series, we would have the, we'd go to the next level, the second derivative of fx with respect to dx evaluated at 0 times x squared over, it's going to be 2 factorial, which is just 2, plus d squared fx by dx dy, 0 times y, right, times y squared over 2 factorial. Sorry, I know it's getting cramped, but the point is that because we're trying to linearize this, we're ignoring the higher order terms. So this, we'll just note, ignore higher order terms. Okay, so yeah, that's 0. And then going back to the rest of the evaluation, we see that x dot, it does not appear at all in the equation for x, so we know that this one is also going to be 0. So we made our work a lot simpler. Now we just have to evaluate 3 of these partial derivatives. So let's go ahead and do that. Let's start with the x value, dfx dx. So we start, there's an x there, so that's going to be a 1. Lx is a constant, so that's 0. Then we have 2y dot. Well, that doesn't depend on x, so that's 0. Then we have this kind of big mess. We have x in here, and we have x over here as well. So we have to use product rule, and let's do the easy version first. Let's see, we'll put in a negative because we know that this whole quantity is going to have to be negative. We'll put a big parenthesis sign. So we're going to have a couple of quantities here. But so by the product rule, this means that this is equal to the derivative of this guy times this plus the derivative of this guy times this. So let's do the first one here. So we know that the derivative of this with respect to x is just going to be 1 because that's derivative of x with respect to x, that's 1. Those are constant, those are 0, so it's just 1. So it's basically just this term. So that's going to be, plus x plus lx plus mu times the derivative of this thing with respect to x. And actually this is a constant, so we could pull this out here. Let's go ahead and do that. So we got that, and then let's see, where were we? Right, we're here. So this is going to be similar. We're going to do minus sign. Just enough room. Good. Okay, so let's take a look at this one. So let's go ahead and write this thing out. Basically, we have to do 2 chain rules here. To make things a bit simpler, I'm going to rewrite this one more time so that we can take the square root, which is, exponent 1/2, and combine it with a 3 and throw in a negative there so we don't have the 1 over. So this just makes it easier for me personally to think about it, but if you're doing this on your own, feel free to do this whatever way works for you. So now we do the derivative. First we do chain rule once, and we're going to get, this is going to be equal to negative 3/2 by to the minus 5/2, right? Because we're just doing power rule here. And then that's going to be multiplied by the derivative with respect to x of everything that's inside of here. So that's, we can see that this is going to be equal to 2x, right? I think that should be pretty clear. This doesn't depend on x, so it goes away. This doesn't depend on x, so it goes away. This one, we sort of do another chain rule, but these are two constants, so it doesn't really change a lot. Basically, what we're going to end up, this is going to become 2 by x plus lx plus mu. Note that this 2 is going to cancel, and remember that this thing to the 1/2, that's r13. So what we're left with is this is going to end up being -3. So similarly, if we look at the derivative with respect to x of 1 over r23 cubed, it's essentially the same math, except instead of x plus lx plus mu, it's x plus lx minus 1 minus mu. So we're going to end up with -3 by... So let's go ahead and plug those back into our equation for dfx dx, and we're going to get to the 5th. Okay. So we have one more thing to do here. We need to evaluate this at 0. So let's take a look at what that's going to look like, and let's bring this one back to see what is this going to look like at 0. Let's take a look. df dx evaluated at 0. That's going to be 1 minus mu over r13 at 0 is going to be, and here we're going to have -3 by, oh sorry, I should note that this is cubed here, minus, for simplicity, I'm going to denote that r13, capital R13, is going to be equal to the square root of lx plus mu squared plus ly squared, and r23 is equal to square root of lx minus 1 minus mu squared plus ly squared. So now we can rewrite this as, so you can see why I refer to this as rather technical and complex mathematics. Like, this was a fair bit of work, and this is just the first partial derivative of the first Taylor series we're working out, because we still got to do df dy and df dz. So let's go ahead and take care of those, and then we'll finally be able to write the first order Taylor series expansion of x double dot around its origin. So dfx dy, let's go ahead and bring back our sheet so we can reference the equation. So this is going to be 0, that's going to be 0, that's going to be 0. This one, it's going to be similar to what we had here, because there's no y in the numerator here, there's only a y in the denominator, so we don't need to do the product rule. We essentially just need to do this same derivative, except instead of with respect to x, it's with respect to y. And you're going to see that it's really similar, because this part's going to be the same, so this part's the same, and this part, instead of being the derivative with respect to x of this quantity, it's the derivative with respect to y of this quantity, so it's going to end up being 2 y plus ly. So let's just go ahead and write these things out to make it a little bit easier. So essentially, we'll take the numerator and we'll pull it out as a constant. So we're going to have, so again, if we look at this, I'll just rewrite it up to here. We're going to see that it's going to end up being 2 by y plus ly. These 2's go away to the 5th. So going back to this equation, we're going to see that dfx dy is equal to, I'm just going to go ahead and combine all the terms here. So the negatives are going to cancel out. So we're going to end up with to the 5th. And so now we're going to want to evaluate it at 0. So, okay, we're 2/3 of the way through our Taylor series expansion of f of x. We just have one more to do. And you'll notice, by the way, since these are being multiplied by ly, that the y coordinate of the Lagrange point, when we go to evaluate the collinear points, this is going to be 0. So this whole term is going to drop out. Don't worry about that for now. We'll come back to it. Let's, for now, continue with our Taylor series expansion, because we have one more to do, and that's in the z direction. You can actually see that it's going to be, pretty much identical to the partial derivative with respect to y, because again, no dependence on z, constant, no dependence on z, the numerator doesn't depend on z, the numerator here doesn't depend on z, so the only thing that depends on z is down there. So it's essentially going to be this same equation here, except instead of the derivative with respect to y of r13 and r23, it's derivative with respect to z. And hopefully you can see from here that derivative with respect to the variable, it's -3 times the variable divided by that thing to the fifth. So I'm actually just going to go directly to here. So when we evaluate this at 0, it's just going to be 0, because z is 0, it's being multiplied by both of these, it just goes away. So that's fantastic. So we can go back to our equation here, and we'll note that this one is 0. So that's great. So now we can finally write our linearized equation for the acceleration in the x direction. So let's see, let's start with our evaluated value of df dx. That's right here, right? That's here. So it's that whole thing being multiplied by x plus the derivative with respect to y evaluated at 0 times y. And I'm going to factor a couple things out of here. And then if we look back at our equations, so the derivative with respect to z evaluated at the 0.0, that was 0. This one is 2y dot, so we get to add. And then the rest is 0. So finally, here we have Taylor series expansion of fx, or the x acceleration, about 0. Okay, so let's keep going with our Taylor series expansions, because we still have to do a Taylor series expansion about y and z. Let's take a look at that one. Taylor series expansion of fy about the 0 vector is going to be equal to fy at 0, which we know is going to be 0 because it's an equal point, plus, so as before, because we're trying to linearize something, we ignore the higher order terms. The equation for y, let's bring that up here. So it doesn't depend on either z dot or y dot, so we know that these are going to be 0. And we know that the derivative with respect to x dot is just going to be -2. So then we just have to do the same 3 that we did before, except evaluated on the y values. So let's go ahead and start with dfy dx. We'll see first 3 terms, no dependence on x, and then here it's basically going to be this thing, partial derivative with respect to x, but we already know what the partial derivative of r13 with respect to x is. So here I'm going to write this at the front just so that we have that, y plus ly. And then let's reference our notes. So we know that the derivative with respect to x of 1 over r13 cubed is -3 times this quantity, and here we have 1 minus mu, so it's just going to be, oh sorry, I was looking at the wrong spot, yeah, 1 minus mu, and I guess I should remember to bring the negative along here. Not too bad, considering we've already done a lot of the work. And so that's it, and we can now evaluate it at 0. Now we can do dfy dy. That one's going to be a little bit more involved, but that's okay, we can do it. The derivative of y with respect to y, that's going to be a 1. That's a constant, so that's 0. That has no dependence on y, so that's 0. So then we get to this guy. So that's going to look kind of similar to what we did here for dfx dx, where we're going to have to do product rule again. So it's derivative of this guy times this plus derivative of this guy times this. So that's the whole thing. And again, we can reference our notes. We know what the derivative with respect to y of 1 over r13 and 1 over r23 is, and we know that in each case they're multiplied by y plus ly, so we're going to have a similar squared term like the ones we have up here. Okay, and as before, we need to evaluate this at 0. Now to finish up this one, we just need to do the derivative of fy with respect to z. So let's bring up fy again so that we remember what it is. Here we go. This thing, derivative with respect to z. Again, it's basically just this whole thing, derivative with respect to z. And from our notes, when we evaluate it at 0, we notice z is going to be 0 in both of these terms. This whole thing is going to be 0, so this whole thing again is going to be 0. So we can write that the Taylor expansion of fy around 0 is going to be -2x x dot. So here we have our Taylor series expansion of y about the origin. So last but not least, we got to do fz. Now I think you've figured out by this point that z, it doesn't depend on x dot, y dot, or z dot, so those terms are all going to be 0. So we can, and we already know this is, that evaluated at 0, it's going to be an equilibrium point. So t fz at 0, so I won't bother writing all of these extra things that we already know about. So that's going to be times z, dfz dx. That's going to be, so I'm just going to go ahead and stop here because I know that I'm going to evaluate this at 0, and I'm going to have 0 times the derivative of something. That's going to be 0, so I already know that dfz dx evaluated at 0 is going to be 0. So that's going to go away. And then by similar logic, dfz dy, that's also going to be 0. So then we're left with dfc dz, which is not going to be 0 at 0. dfz dz. Once more we do product rule, so that's going to be minus z times the derivative with respect to z of this same thing. And again, we're going to evaluate it at 0, so this term is going to go to 0. So this is the only one we actually care about right here. So we can just say, and so now we can write the Taylor expansion of fz at 0 times z, which looks surprisingly like the original equation for z, except for the fact that we've linearized it by virtue of the fact that we've made r13 and r23, which were functions of the position. We've turned them into constants. They're constants that need to be evaluated at the specific Lagrange point, so it's kind of funny because it's like simultaneously a function and a constant, but the thing is, we're going to be evaluating these at each Lagrange point in turn. So when we're evaluating it at a specific Lagrange point, these two are going to become constants. Okay, now that we have finished doing our Taylor series expansions, we can start doing some stability analysis. First, let's rewrite our equations in a somewhat more convenient form. We're going to note that x double dot is approximately equal to, now I write approximately here because we did a Taylor series expansion. It's kind of a subtle point. In all of these examples, I've used equal signs because these are equals values, right? The Taylor series expansion of fy at 0 is equal to this. The partial derivative of fy with respect to z value at 0 is equal to 0. But in general, Taylor series, we've done an approximation, right? So that's why I'm noting here that this is the actual x double dot, but it's approximated by our Taylor series expansion. And I want to write this in a more convenient form because this is a lot to write. So what we're going to do is we're going to refer to this part as fxx, i.e. this was the partial derivative of xx with respect to x, so we're going to call it fxx. And then this part that's in front of the y, we're going to denote this as fxy. So then the x acceleration is approximately equal to fxx times x plus fxy times y plus 2y dot. Similarly for the y acceleration and the z acceleration. So remember, these are constants. They depend only on which equilibrium point we're looking at, but since we're only looking at one at a time, these are constants for all that value. So the thing we notice right away is that the z value is decoupled from x and y, and so we can actually analyze the stability of this separately. And we know that fzz, oh, I made a mistake here. This should be a plus. My apologies. So we know that this is always going to be a positive quantity, right? Because mu can only range from 0 to 0.5. If you look at the equation for mu, you'll notice that the smallest value the second primary could have, it would be epsilon, right? Some epsilon greater than 0, because if it's 0, then it's no longer a two-body system. But it could be some fraction above 0, but it can only get up to 0.5 or rather the value of mu can only get up to 0.5, because once m2 reaches half the value, more than half the value of m1, well, now it becomes m1, right? Because we're treating it such that m1 is always the heavier body of the two bodies, and m2 is always the smaller one. So the most this can get up to, if m2 is equal to, if they're both 0.5, right? If the mass is both 0.5, then it's 0.5, 0.5, 0.5. So that's just 1/2. So that means that this quantity, despite the fact that we're subtracting something, this is going to range from 1 to 0.5, and then this is going to range from 0 to 0.5. So this is always positive, but because there's a negative sign, it means it's always negative. So then if we look at the characteristic equation of z, so we're going to have z double dot minus f z z z approximately equal to 0. So the characteristic equation of this is going to be r squared minus f zz. Well, that means that the roots are going to be plus or minus the square root of fzz. So because fzz is always negative, we know that this is imaginary. So this is plus or minus some constant value k times I. So essentially we're saying that in the real imaginary plane, on the z-axis, we have center points. So we have plus or minus I. So as we mentioned earlier, the Hartmann-Grobman theorem tells us that if we have center points, then we can't reach any conclusions about stability, because we don't know if the higher order terms are going to push these to the left or to the right. Here, actually, we can sort of take a step back from all of the rigorous mathematics and just take a look at the equation. So here's the thing. We know that R13, we know that, just like this is the nonlinear equation that we're looking at here, and just like the linearized equation, this thing is always positive, which means that this term is always negative, and what that's telling me is that the acceleration in the z direction is always opposite of the z position. So if the z position is positive, meaning you're above the plane of the two primaries, then your acceleration is going to be negative. But once you get below the plane of the two primaries, your acceleration is going to be positive. And that's true regardless of where you are. So even though this equation is nonlinear, we can see, we could have actually seen this without doing the Taylor expansion, but I wanted to do the Taylor expansion of z just for the sake of completeness, at least in that case. So we can see that motion in the z direction is going to be oscillatory. It's basically going to keep going up and down the plane, which makes sense when you think about it, because we have two bodies, they're orbiting each other in a particular plane, and when you're above the plane, the sum of the forces in the z direction is pointing down if you're above the plane, and when you're below the plane, the sum of the forces is going to be pointing up. So it's just always going to be like that. It's going to be like a spring. It's a nonlinear spring because the strength of the spring does depend on these R13 and these R23 terms, but it's still essentially a spring, so we know that it's marginally stable. So that's cool. So at least in the z, we're stable. Now how about in the x and y direction? Here, we're going to want to put this into matrix form. We're going to change up our state vector a little bit, our capital X state vector. We're now going to say that it's equal to x, y, x dot, y dot. Because we've already looked at the z and we've seen that in the linearized case, the motion is decoupled, right? These fxx, fxy, they don't have any dependency on z at all. So we'll write this, sorry, it's going to be transposed. So we'll write this in matrix form. This is now our x dot on the left, our state vector x dot. And so now we're going to populate this matrix. X dot is simply equal to x dot, so that just gives us 0, 0, 1, 0. Y dot is just equal to y dot, so that's 0, 0, 0, 1. And then x double dot, it's fxxx plus fxyy plus 2y dot. And then y double dot, fxy, fyy, negative 2x. So now we have a linear or linearized system of equations. And to look at their stability, we need to take a look at the eigenvalues of this matrix. Now we're going to do this purely analytically. So the algebra is going to get a little hairy, but bear with me because we'll be able to reach some pretty rigorous conclusions here, and we'll be able to paint that richer picture that I talked about at the beginning. So we've written this in the form x dot is equal to ax. We want the eigenvalues of a. So the eigenvalues are the solutions to the equation, the determinant of a minus lambda I is equal to 0. So the determinant of a minus lambda I, let's take a look at that. So to take the determinant of this matrix, we can use this trick where we know that it's going to be negative lambda times the determinant of this 3 by 3 matrix, right? Like you sort of block out the row and the column, and you multiply the determinant of whatever is left by the element that you blocked out. And then it's going to be minus 0 times the determinant of this 3 by 3, which is of course 0, plus 1 times the determinant of this 3 by 3, this 3 by 3 essentially, plus 0 times the other one. So let's write that. It's going to be, so let's write that out. That's going to be, let's combine some terms, do some algebra, reduce a bunch of things, make this look a little bit prettier. So then these terms are going to go away. We're going to end up with, this actually works out really nicely because lambda is our variable. We have to the fourth and to the squared. We don't have a cubic or a linear term. So we're going to say big lambda is equal to lambda squared. So then, by the way, lambda is going to be equal to plus or minus the square root of big lambda. And so we can rewrite this equation as, and then from here, we'll be able to use the quadratic formula to look at the roots. So let's go ahead and write that out actually. So we know that big lambda is going to be equal to, these are the roots. Well, the roots are actually plus or minus the square root of this. Now I know it looks like scary and forbidding, but things are actually going to drop out in a fairly straightforward fashion. Let's start with taking a look at the collinear points. Note first of all that fxy is going to be 0. So we alluded to this earlier. This term is our fxy, and notice that fxy and fyx, they're the same. At the collinear points, so this is lx is not equal to 0, and ly is equal to 0. So fxy, that's just going to be 0. And for fxx and fyy, the thing is, we don't have to show exactly what they are. So we know that fxx is always going to be greater than 0. Now, fyy, it's not as clear, right? We have a positive term and we have two negative terms. Are these negative terms going to outweigh the positive term? Are they going to always outweigh it? Sometimes, never? So it's difficult to show algebraically, but you can show numerically that fyy is always going to be negative for all values of mu and all values of L sub x. I'm not going to do that right now because I don't want to break the flow of us looking at these eigenvalues, but I will show you in an appendix video how we can show numerically that fyy is always going to be less than 0. What that comes to though is that right here we look at this equation and we know that fxy is 0 because we're at a collinear point. And we have a quantity that's always positive and a quantity that's always negative. And so this thing, minus 4, positive, negative, this is going to end up being added to this term. So we know that the quantity under the radical is always going to be positive. That's useful because it means that lambda is of the form negative b plus or minus the square root of b squared plus k, where k is some constant greater than 0. Basically, we know that this negative 4xy, that's our k, right? It's always greater than 0. So when we have negative b plus or minus a value that's slightly greater than b, because we know that this is slightly greater than b, right? Square root of b squared plus some constant, it's slightly larger than b. So that means that negative b plus some quantity that's slightly larger than b means that's going to be positive. Negative b minus some quantity that's the size of b, that's still going to be negative. So here we can say that lambda 1 is going to be greater than 0, and lambda 2 is always going to be less than 0. And this is true for any of the collinear points, L1, 2, or 3. Now, you might wonder for a second, well, we don't know if b is positive or negative, because this one's positive and this one's a negative. How does that work out? But it actually doesn't matter, because it would just flip the sign here, right? Because we have negative b, say b is negative, then minus a negative, that means that this is a positive value. Well, a positive value plus a positive value is going to be positive. A positive value minus a value that's slightly larger than the value itself, that's going to be negative. So we know for sure that one of these roots is positive and one of the roots is negative. So that means that lambda 1 and 2 are going to be plus or minus the square root of lambda 1, and lambda 3 and 4, little lambda now, is going to be plus or minus the square root of lambda 2. So these are the actual eigenvalues of our linearized system. Well, what that tells us is that because lambda 1 is positive, we know that small lambda 1 is going to be positive, right? Because it's positive the square root of a positive number. Little lambda 2 is going to be negative. Right, it's going to be negative because it's negative the square root of a positive number. And then lambda 3 and 4 are going to be imaginary. And here we start to see that richer picture that I was talking about. We know that one of the poles of our linear system is in the right-hand side of the complex plane. Lambda 1 is greater than 0, so we know that the system is unstable. We know that the linear system is unstable, and by extension, we know that the nonlinear system is unstable by that same Hartmann-Grobman theorem that I mentioned earlier. And then we see here that we have these two imaginary points. Now, I know we said that if a pole is imaginary in the linear system, you don't really know what it's going to look like in the nonlinear system, but it's going to be kind of close, and that's actually where we see that those richer dynamics. So with those balls that were bouncing back and forth, they were basically triggering this mode. So they were on the imaginary mode. Now, eventually this mode took over because the natural dynamics there are unstable. But we're going to use these imaginary roots to be able to construct equations that let us get onto those oscillatory solutions and find ways to stay there. So we're going to use these imaginary values to find ways to construct initial conditions that let us get onto those oscillatory solutions and get back to them when we start to deviate from them a little bit. We're not going to do that just yet though, because we're going to take a look at the stability of the equilateral points real quick. And then that's going to be it for this video lecture. In the next video lecture is when we're going to start taking a closer look at these, seeing how we can construct those initial conditions and plotting some actual halo orbits. So stay tuned for that one. It's going to be great. Let's take a look at the equilateral points. Referring to our previous slides, the exposition for the equilateral points is x2 minus x1 over 2, but we've already figured that x2 is equal to mu and x1 should be Lx. x2 is equal to mu and x1 is equal to 1 minus mu. This ends up giving us 1/2 minus mu. And Ly we had discovered was plus or minus the square root of 3 over 2 times L, but we've non-dimensionalized things in here, so the L goes away, so we just get plus or minus square root of 3 over 2. All right, let's calculate fxx, fxy, and fyy, the equilateral points. Let's start with calculating r13 and r23. So r13, square root of Lx plus mu squared. So Lx is 1/2 minus mu plus mu squared plus Ly squared, which is, I'm going to drop the plus or minus because that's it's getting squared, so that's going to be 3 over 4. We end up with square root of 1/2 squared plus 3/4. Well, that's just going to be 1. That's rather nice. And then r23 is going to be, so again, that's equal to 1. So that's nice. So that means that as we go to evaluate all of these quantities, the denominators are just 1. So that's going to make the math get a lot simpler, which is great. So let's take a look at fxx. So we're going to have 1 minus mu minus 3 times Lx plus mu. Well, we figured out here that Lx is 1/2 minus mu, so Lx plus mu is just 1/2 squared times 1 minus mu minus 3, and that one we figured out from here is just negative 1/2 squared, so that's just, again, 1/2 squared times mu. So that's going to be 1 minus, these go away, so fxx just becomes 3/4, which is pretty nice. Let's take a look at fxy. That's going to be 3 over 2. So let's see, what do we get there? It's going to be plus or minus, so we end up with plus or minus 3 root 3 over 2 by 1/2 minus mu. Okay. And let's do fyy. Here's our fyy. So that's going to be 9 over 4. So that's it. So we have fxx is equal to 3 over 4, fyy is equal to 9 over 4, and fxy, it's a little bit more complicated, but it's still relatively simple. So let's go ahead and plug this into our large equation for big lambda here and see what we come up with. All of that's going to be divided by 2, which isn't really that important, so we might drop it in a bit. But anyway, 4 minus 3/4 minus 9/4. Let's minus 12/4, which is minus 3, so that's 1. So that's nice and simple. So we get lambda is equal to minus 1 plus or minus square root. I'm actually just going to bring the 1/2 up here. Oops, not a, big lambda. 1 minus, there's kind of some ugly fractions going on here, but I think we can simplify things because I see that 3 times 9 is going to be 27/4, and then a 1/2 squared is also going to give us a 27/4. So let's take a look at the value under the radical here, and let's see what the possible values for it are, because that's going to tell us what our roots can be. So if we have, let's call this value, let's call this function s as a function of mu. So we have s of mu is equal to 1 minus 27 mu by 1 minus mu. So we know that mu ranges from 0 to 1/2. So I have greater than 0 instead of greater than equal, because if mu is exactly 0, then the mass of our secondary is 0, and so we no longer have a two-body system there. So let's take a look at what s looks like at those values. So s at 0 is going to be, well, it's 1 minus 27 times 0 times something, so it's just going to be 1. So in that case, we're going to have negative 1/2 plus or minus 1/2. So the roots are going to be 0 and minus 1. So we have no conclusions about stability there, because square root of 0 is just 0. Square root of minus 1 is, of course, I. So we have 0 and plus or minus I as our roots. So there's nothing in the left-hand side of the complex plane. There's nothing in the right-hand side of the complex plane. So because we've linearized this, we can't actually reach any conclusions about stability in that case. Let's take a look at what does S look like when mu is 1/2. 1 minus 27 times 1/2 times 1 minus 1/2. So that's going to be a quarter. So it's going to be equal to 1 minus 27/4. So that's going to be very negative, right? That's going to be negative 23/4. So that means that this value here is imaginary. So in that case, we have a complex number here. Big lambda is a complex number, and when we take the square root of a complex number, we get another complex number. So here we have plus or minus a complex number, plus or minus a complex number. In that case, because complex numbers have a real part, we have plus or minus a real part here and plus or minus a real part here. So that means we're going to have 2 unstable roots and 2 stable roots. So now that we've looked at what happens at the extreme ends of the mu range, what happens in the middle? Well, when mu is slightly greater than 0, s will be slightly less than 1. So we'll have negative 1/2 plus or minus something smaller than 1/2. So negative 1/2 plus something smaller than 1/2 is still going to be a negative number, and negative 1/2 minus something less than 1/2 is still a negative number. So both big lambda 1 and big lambda 2 are going to be negative, which means that little lambda 1 and little lambda 1, 2 and little lambda 3, 4, those are all going to be purely imaginary. So we have marginal stability in the linear sense, but of course we can't reach any conclusions about the nonlinear system because we don't know if the higher order terms will push these center points to the left or to the right, or maybe even keep them in place. But there's one more thing that's worth looking at here, and that's, that starts out positive and it becomes negative. So at what point does it cross over? Like, when is it equal to 0? Let's consider s of mu is equal to 0, so that's equal to 1. We can turn this into a quadratic. And when we throw this into the quadratic formula, we're going to end up with 2 roots. We're going to have mu is equal to 0.961479, and mu is equal to 0.03852, and so on. So this one's invalid because mu can only range from 0 to 1/2, so that's not a valid root. But this one is valid. So that's saying that below values of mu of 0.038, we have this neutral stability where we don't have any unstable terms, we don't have any stable terms. And I would bet that a Lyapunov analysis would show that those points are marginally stable. and I may do so in an appendix video, but what's important to know is that for most values in the solar system, they're going to be less than this. So mu of Earth Moon, that's equal to 0.012. Mu of Sun Earth, that's equal to 0.302, something. So way below that one. Even Sun Jupiter is 0.009 and so on. So you can see that for most of the cases in the solar system, the values are below this critical value, and so they have this marginal stability. Okay, wow, that was a lot of math. If you made it this far into the video, please leave an integral sign in the comments, and please hit the like button as well. Thank you so much for watching.